here we're going to let f of x equal 3x plus 12. In a straight line. And we want to find the equation of the inverse of f. So if y equals 3x plus 12, first thing we do is switch our x and y values. So x equals 3y plus 12. Subtract 12 from both sides. X minus 12 equals 3y. And we divide by 3 on both sides. That's the old equation. And come up with y equals x minus 12 divided by 3 as our inverse relationship. Now we're asked to plot them. So y equals here, I've put in my two equations, 3x plus 12 and x minus 12 divided by 3. If we look at the graph, the standard window, we can see that that steep line is 3x plus 12, and the less steep line below is x minus 12 divided by 3. Question we're being asked now is f an invertible function? Why or why not? So what does it mean to be an invertible function? It means that our inverse relationship turns out to be a function as well. So let's look at our graph. That lower line there is our inverse relationship. And we can see that that lower line passes the vertical line test. Every x value has only one y value associated with it, so our inverse relationship is also a function, which means that our original function is invertible. The next thing we're being asked is to show algebraically that the composition of the inverse of f with f is equal to x. Let's give that a shot. So, first let's clear our screen here. Now, first thing we do is we take f of x, 3x plus 12, and we insert that information for x in our inverse relationship, which we can see is x minus 12 divided by 3. So x now becomes 3x plus 12. And it was x minus 12. And all of that divided by 3. And this will give me a composite of the inverse of f and f of x. So let's simplify. 3x plus 12 minus 12 all over 3. And that becomes 3x over 3, which is equal to x. So we've shown that algebraically. Now, just a quick side note, invertible functions are also called one-to-one functions. They're functions that either are strictly increasing or strictly decreasing. So what that means is that for every x, there's only one y, and every y, there's only one x. In other words, our function passes the vertical line test and a horizontal line test. Our line only crosses the graph once, whether it's vertical or horizontal. So again, as a quick recap, the inverse of a relation in two variables is formed by interchanging the two variables. When we do that, we end up with a graph that is a reflection of the original function over the line y equals x. If the inverse of function of f is also a function, we'll use the term invertible. And if f is invertible and y equals f of x, then you can write the inverse using this notation, y equals f to the minus 1 of x. That doesn't mean 1 over f of x, it means the inverse. All right, and to plot the graph, we have two approaches. We can interchange the variables and solve for y again, and plot that equation or equations if necessary. Or we can simply use parametric mode and take advantage of the fact that we can switch our x and y information simply with a couple of keystrokes. finally, the relationship between an inverse and the original function. When we take a composite of the two, it should always resolve to x. As long as x is in the domain of f, and f of x is in the domain of the inverse of x. That refers back to an earlier lesson where we discussed how a composite function could result in an error from our calculator because of domain violations. And the same relationship holds true if we take f of f inverse instead of f inverse of f. And remember, a one-to-one function is invertible. Strictly increasing or strictly decreasing functions are one-to-one functions. All right, that sums up lesson 1.5.